Okay, now we're recording. Now let's bring up everything here.
Hey, you, wearing guacamole. Brazil Pro Clean can tackle that part.
Okay, wow. There he is. Gotta love it. Good old Starman.
I must say, the SpaceX spacesuits are pretty aesthetic. They definitely took that into account for design.
Yep. Okay, so today is all about Kirchhoff's rules. There are two rules that Kirchhoff came up with that involve two laws of physics. And the two laws are the law of conservation of charge and the law of conservation of energy. So we'll start with the law of conservation of charge, and that involves what we call Kirchhoff's first rule, or the junction rule. And what the junction rule says is that if you go to a particular junction of three or more wires or components in a circuit where they come together and connect together, then the sum of all the currents, all the different currents that are entering that junction have to equal the sum of all the currents that are leaving that junction. So if you're looking at this circuit, for example, you have two places where you have a junction. This one right here and this one right here. And what this rule means is that any currents coming into this junction also have to leave this junction, and current can't just escape somewhere else. That's really what all the rule means. It means that charge coming in has to equal the charge going out, or current coming in has to equal the current. It's pretty simple. It's like an intersection of cars. Cars coming in have to equal cars coming out, unless you have an accident and they stay in the intersection, I guess. But it's a fairly simple law, and it is true. It always should be true. So we can hold that to be true. So Kirchhoff's first rule is the junction rule. The fact that we say that all the current coming in has to equal all the current going out gives us the opportunity to build an equation. So if we label the currents at this junction, there are three separate wires at this particular junction, and if we label each of these different wires with a current, I1, I2, I3, for example, then we could make an equation that says something like I1 plus I2 equals I3, or I3 plus I2 equals I1, or whatever. But we would have to know which way they're going, wouldn't we? Actually, we don't. Because it's an equation, if we just choose the way the currents are going, and then put them in the equation as if we knew, so we just say that, let's say the current from resistor 2 we'll call I2, the current from resistor 1 we'll call I1, and the current on this other one we'll call I3. So let's just say that that's what we call them, and let's say that I3 is coming in, R1 is going out, and R2 is going out. But we'll just choose them that way, and we'll label it that way. Because it's an equation, the equation automatically assigns those currents a sign in the equation. In other words, if we put all the currents on one side, the currents going in would have the opposite sign of the currents going out. And then at the end of the day, when we solve the equation that we have for the currents, they will either have negative signs or positive signs. And guess what? Current is always positive. So if it comes out negative, we know that we chose the wrong direction. And we just flip it around. We flip the direction around. It's really quite simple. So it's beautiful. So with Kirchhoff's laws, the first thing that we do, with Kirchhoff's rules, with the junction rule, the first thing that we do is in each branch of the circuit. So any part of a circuit that is between two junctions. So this right here is a branch, this place where R1 is. This all the way around here is a branch, and this all the way around here is a branch. In each branch of the circuit, we define the current. We give the current a name in each branch of the circuit. I1, I2, I3, or whatever. We give each branch its own current and give it each one of those currents its own name, and we choose a direction for that current. Doesn't matter if we're right or wrong, just choose a direction. Okay, and we're good to go. And then in the end, we'll be able to use that information mathematically to figure out which directions they're actually going, depending on what sign we get for the current for each of those currents when we solve them in the end. But Kirchhoff's junction rule is not always enough we don't always get enough information from the junction rule to solve for all of the things that we don't know in a particular circuit. Usually in a circuit, the things that we know are the resistors and the power supplies and the capacitors and the diodes. We usually know the components that we've put into the circuit. But what we usually don't know is what all the currents are going to be and what all the voltages will be everywhere. And so those are the things we're trying to solve for. The loop rule, or sorry, the junction rule will help us solve for the currents in particular. And so that's good. However, how are we going to solve for voltages? And if we don't have enough information from that junction rule to solve for all the currents, how are we going to solve for the rest of the currents? Well, the second rule is going to help us do that. It's called the loop rule. And in the loop rule, we take advantage of the conservation of energy law, which in a circuit says that if you start at a point and go all the way around a loop, and you calculate the potential difference or the potential change every time you cross a component in the circuit. So the resistor going across the power supply, going across another resistor. Every time you go across one of these things, you're going to have a change in potential, either up or down. There'll be a positive or negative change. And when you get back to the same point that you started from, what should that total change equal?
0.
Why?
Because you're at the same place.
That's right. When you go from one point on a circuit back to that same point, it has the same potential at that point. So the change in potential has to equal 0 because you've come back all the way to where you started from. And so that gives us another chance to write an equation. We add together every potential change, and then we set that equation, set that mathematical expression equal to 0. So another equation. So this becomes a practice of building equations, multiple equations, and then solving multiple equations simultaneously for multiple variables. Don't we love that kind of math? Of course we do. The total number of possible equations that you can build must be more than the total number of variables that you have, otherwise you'll be in trouble. You won't be able to solve for all of your variables. So it's a good idea to be able to build as many equations as you can. So let's put this into practice. Let's do a very simple junction rule. Here's a junction where we have 3 currents coming in. 3 currents at a junction. 1 current coming in, 2 coming out. The one coming in is 11 amps. The one on the top is 7 amps. The one on the bottom is 4 amps. And so the one coming in should equal the 2 going out. Easy. Sure it does. That's fine. But the second rule is not so simple. We're just going to do a very simple thing, a very simple circuit that only has this single loop in it. But it's not so simple figuring out what these potential drops are. And we have to do some thinking about this. So, what is potential, first of all? Remember that potential is related to potential energy, so that the potential across a particular circuit element is dependent on some things. Essentially, you look at the element and you say, is this element going to increase the potential in the circuit, or is it going to decrease it? Well, a battery is pretty easy. If you go from the negative side of a battery to the positive side of a battery, you're going to increase the potential in the circuit. The potential is going to increase no matter what. So if you're going from the negative side to a positive side, it's going to increase. If you're going from the positive side to the negative side, it's going to decrease no matter what. So that's the rule for batteries and power supplies. Going from negative to positive, it's going from low to high. That's an increase in potential. That means that part of the potential change is going to be a positive value. And you have to make sure that you know that. If you're going from positive to negative, it will be a negative value. And what will that value be equal to? It will be equal to the voltage of the battery. And remember when we talked about voltage of batteries, we talked about the EMF of the battery. Because here the battery is listed, it's got next to it its internal resistance. That little R next to it is the internal resistance of the battery. So the battery here is considered a battery. This little representation represents the battery without any resistance. So we use the EMF of the battery, and then we go through the internal resistance of the battery later and take that into account later. So the EMF, if we go around this loop in a clockwise direction, we're going to be going from the low side to the high side. With Kirchhoff's second rule, you can choose which way you want to go around the loop. It doesn't matter which way you go, but you have to choose that way and stick with it. Because that's going to determine a lot of things. First of all, it's going to determine which way you go through the battery, right? And that'll determine whether or not your EMF is positive. In this case, it is positive, so EMF is put into the equation as a positive EMF. Otherwise, we would put it in as negative EMF. Okay? Now, for the rest of these things, it's always going to depend, for the resistors in this equation, it's going, the sign of the potential difference is going to depend on the direction of the current. Now remember, back when we were doing Kirchhoff's junction rule, we chose directions for the current. And in this case, you're going to use those directions that you chose to determine the direction of the current here. So if we chose the current to be going from left to right on the top of here, that means that the current is going clockwise with us as well all the way around, because there's nowhere else for the current to go, right? And in this case, they did. They've chosen the current to be going this way, which is the way the current is going, incidentally. But it wouldn't matter if we didn't know which way the current was going. If the current was going who knows which direction, and we didn't know, we would just choose the current in between points, and then we would use that in both laws. But in this case, we're choosing the current to go the same direction as we are going around the loop to create our equation. And as we go through each resistor in the direction of current, what happens to energy in a circuit if you're going in the direction of the current? What happens? It does. As current goes through a resistor, it loses energy. It loses voltage. So it goes down. That means the voltage drop will be negative through the first resistor, the second resistor, and the third resistor. If we decided to go backwards, and you can decide whatever way you want to go through the loop. If we wanted to do our loop for Kirchhoff's loop rule backwards and go counterclockwise, then we'd be going against the current. And all of these voltage drops would actually be positive. It'd be like we were swimming upstream and we're swimming against the current. And the change in potential would actually be positive across each resistor. And then all of these things would be positive and the EMF would be negative because we'd go backwards through the battery. But it would give you the same equation. It would just change the sign on everything and the other side's zero, so it doesn't matter. So, in order to apply Kirchhoff's rules, we have to do a couple of different things. The first thing we have to do is we have to choose the direction of the current in each branch. So you go to, you mark your, mark the junctions in your circuit. So we have a junction A here and a junction E over here. They've labeled them as. And those are the only two junctions. They're the only two places where 3 or more elements are connected. Okay? If you're at each of those junctions, between each of those junctions, there is a branch of the circuit. So there are 3 branches. There's this top branch, this middle branch, and this bottom branch. The top branch, we're going to choose a direction for the current. Going from A to E, we're saying that the current is going up this way and around and back down. So it's kind of going, just for this top branch, it's going clockwise. I hate to say clockwise because this middle branch is not part of that. But we've chosen this to be going this direction. We've chosen it to go out of A and into E, in other words. In between A and E and this middle branch, we've chosen the current to be going from right to left. We don't necessarily know which way the current is going there, or anywhere else for that matter. It doesn't take, you don't have to be very complicated in a circuit to get to a point where you have no idea which way the current is going. And with 2 batteries in here, we have no idea which way the current is going anyway. It could be going any which way. So we've just chosen it to be going from right to left. In between, we've called this top one I2. We've called the middle one I1, current 1. And then the bottom one we're choosing to be going also counterclockwise along this bottom branch. And that's fine too. You could have chosen them all the other way, or you could have chosen them completely different any way you want. There's a lot of choices. But this is just the way they've chosen it. Now, once you've chosen those currents, you have to stick with them through the whole problem. You have to assume that that's the direction until you're done. And you've solved for the current, and it actually tells you which way you're going. Otherwise, you'll confuse yourself. But then after we've done that, we want to choose which way we want to go around the loops. Now there are two loops. There's a loop here. There's actually three loops in this. There's a loop here, there's a loop here, and then there's a loop all the way around the outside. Usually when you have loops that overlap, you don't have to use more than one overlapping loop. So this outside loop overlaps both loops, and these two inside loops overlap each other. So using the two inside loops that overlap each other is enough. You wouldn't necessarily have to use the outside loop and both inside loops to get enough information. But you can
figure out both the inside loops, you know, the whole picture.
you should have enough information to figure it out. And if you don't, just you find another loop. You know, that can be done too. But in this case, we have 3 total loops, and we'll use 2 to start. And let's actually do the rules. The first rule is easy. You go to one of your junctions, doesn't matter which one. In this particular circuit, either junction A or junction E will give you the same equation. If you use A, then you have current 2 going out and current 3 going out, current 1 coming in. So that tells you that current 1 equals current 2 plus current 3, right? Which is the equation we get right here. If you use this one, it gives you the same one. Current 1 is going out, currents 2 and 3 are coming in, so current 2 plus current 3 equals current 1, same equation, right? So it gives you the same equation either way because of the simplicity of the circuit. More complex circuits will give you many, many more equations using the junction rule. But this circuit only gives us one equation from the junction rule, and that's fine. So we'll make that equation and we'll set it aside for now. We'll use it later. Then we go to the loop rule, and we're going to sum up the sum of the equations in the loop A, B, C, D, E, A. A, B, C, D, E, A. So that's this top loop, right? We're going to go through this top loop, and we're going to go through it in a clockwise direction. I like to always choose the same direction, clockwise. Clockwise is just easy to remember. I go through every loop clockwise, so I never forget what I'm doing. And it doesn't matter which way you go through the loops. So if you just choose one and stick with it, then you never have to remember which way you went to figure out if you got your signs correct. So now we're going to go through our loop in a clockwise direction and figure out the voltage drops with the signs and the mathematics. The voltage drop across each one. So in this case, they actually immediately jump to, well, they did this in the example as well, or previously as well, and I didn't point it out. When you do a voltage drop through a resistor, you use Ohm's law, V equals I times R. So it's the current that is going through the resistor times the resistor, and then the sign that you use from the law. If you're going with the current, the sign is negative. If you're going against the current, the sign is positive. Think of it like a river. If you're going with the current in a river, you're going down the river, downhill. So that's down, that's negative. If you're going against the current, that's like going uphill, so it's going to be a positive change, right? And of course, if you go through the battery from negative to high, low to high, then it's positive. From high to low, it's negative, and so on and so forth. The first thing that they go through is resistor 2. So we come up here to our diagram where we have labeled the currents. Do not forget to label the currents. We label the currents, and I usually put a little curly Q arrow in here that shows that I'm going around clockwise. So I'm going from A, and the first thing that I encounter is the resistor, and I look that I'm going through the resistor in the same direction as the current I2. So my voltage drop through here will be the resistor times the current I2, and the sign will be negative. Negative R2, I2. And that's what they've got. Negative I2, R2 right here is their first voltage change. Then they go through the battery. It doesn't matter which way the current is going when you're going through a battery. If you're going from low to high, it's positive. High to low, it's negative. So we're going from low to high. That's a positive change in potential, and it's equal to the EMF of the battery, EMF 1. Then we go through the internal resistance of the battery in the direction of the current, I2. So again, that's a negative drop, and it's going to be I2 times little r1. I2 times little r1 with a negative sign. Then the last thing that we go through is resistor 1, but resistor 1 isn't current 2, it's current 1. So it's going to be current 1, we're going in the direction of current 1, so it's going to be negative R1, I1, and that's the last thing that we have here, negative I1, R1. And that is our equation that has to equal 0 for Kirchhoff's loop rule for that first loop. They go ahead and they do some simplification here. Since we have two things that have current 2 in them, they combine those two things as one thing and then add the EMF and subtract off the I1R1 at the end. So they've created a simpler equation. That's fine. But that's in another equation that we've got. So we've got the first equation from the junction rule, the second equation from the first loop rule that we've done. We've got 2 equations, but the problem is we already have 3 unknowns, right? We have 3 currents that we don't know. So we need to figure out those 3 currents. We need to figure out the third current. So we go around the second loop down below. The second loop down below is, we're going to start at A and we're going to go around, and I think they go around in clockwise direction again. Let's see, A, B, C, D, E, F, G, A, E, G, H, A. Actually, they're going to go all the way around the outside loop is what they're going to do. And that's fine. So you could have chosen the bottom loop or the outside loop. You just have to choose 2 loops that overlap each other somewhere. I wouldn't have gone around this outside one because it's going to make a more complicated equation. Going around this smaller one would make a simpler equation because it has fewer things to go through. But that's just, you know, neither or another. So they're going to go all the way around this, which for the first part of the loop is going to give you the same first 3 elements, right? It's going to give you I2, negative I2, R2, the battery, negative I2, R1, and then you'll come down here and you're going to go through this resistor 3, but now we're going against the current. We're going against current 3 through resistor 3, so that's like going up the river, so it's going to be a positive I3, R3, and then we're going to go through resistor 2 against current 3, so it'll be a positive I3, R2. Then we're going to go from the top, the high end of the battery down to the low end of the battery, so that'll be a negative EMF of battery 2, and then we'll go back to A and that will be done. And if you see their equation here, they have the same stuff at the beginning. No, wrong equation. They have the same stuff. Oh, sorry, no, they did do the smaller loop. I was looking at this thinking that they went all the way around the big loop, but they say we could have done this. They did actually go through the smaller loop. That's fine. Let's go back and do that one. Sorry. So just going through the smaller loop, A, E, F, G, H, A. If you go from A to E, you're going through 6 ohms against current 1, so that's negative. Sorry. If you're going against the current, it's positive I1 6 times R1, so positive I1 times R1. And let's see if that's what they do. It's positive I1 times R1 right there. And then they go through I3, R3 against current I3 again, so that's positive I3, R3. Positive I3, R3. And then they go around this one, which is against current 3 through R2, so positive I3, R2. Then they go through the battery backwards from high to low, so that's going to be negative the EMF of the battery 2, negative EMF 2. And then they simplify that equation and set it equal to 0. And now we've got 3 equations. We've got this equation, and this equation, and we have 3 unknowns, I1, I2, and I3. Right? So, we can use these equations to solve for those 3 unknowns, hopefully. Hopefully they're independent equations and that they're sufficient to solve for these equations. And you'll find out that they are. If you do some substitution, you could substitute these 2 equations into this one, or one of these into the other, and then that one into the next. There's lots of different ways to do it. In this case, they substitute I don't know what they do actually, how they solve it. But essentially what you want to do is substitute so that you eliminate one variable and then eliminate another variable. It's just solving multiple equations, multiple unknowns, something we've done before. But they do it again and again and again until they get one variable, and in this case they solve for I1 first. They end up getting an equation simplified down so that it only has I1 in it by substituting other equations into, actually what they did is they substituted the 2 bigger equations into the junction rule equation in the end. And they get an equation that only has now current 1 in it, and they solve for current 1, right? once you've solved for current 1, you can plug that into one of the previous equations and solve for current 2. Then you can plug both of those into an equation to solve for current 3. And then you can, once you have all the currents, then you know everything in the circuit about the currents. And then once you know all the currents, you can calculate all the voltages, because every voltage across every resistor is just that resistor times the current going through it. And so you can solve for everything in the equation. But notice one thing here. Notice that when we solved for current 2, we got a negative 3.5 amps. There's no such thing as negative current. So what does that tell us about the direction that we chose for current 2 up here? We chose the current to be going this way, but it's actually going this way, right? And that's why it's a little tricky when you have multiple batteries and multiple branches and loops in a circuit. This battery, it seems like this battery would drive the current this way, but it doesn't. This battery down here overpowers it and drives the current backwards this way. So the current is actually going backwards through this battery. And that happens in circuits.
Wouldn't that make that more or less like a battery charger?
It could be, yeah, that could be it. So here are the steps. Take your diagram, your circuit diagram, label all the known and unknown elements like resistors and batteries and things like that. If they're unknown, just give them a number, R1, R2, give them a name. If they're known, you can give them a name also, but you should write in the value so that you know that that one is actually a known value. Then apply the junction rule to all the junctions, right? And get as many equations as you can and set them aside. Check to see if any of your equations are the same equations so that you don't try to use them twice. If you try to use the same equation twice, it'll just waste your time.
Yeah, but the one thing I didn't understand on this is wherever you did the junction rule, right? Where did you get that amperage from?
You don't know the current. You're just saying that the current coming in has to equal the current going out. When you use the junction rule, it doesn't tell you what the current is. You're just assuming that the current is going in and going out, because it has to be either coming in or going out, and all the current that comes in has to equal all the current going out.
But you can't prove or disprove it until you know.
No, you can. That is not a thing that you prove. That's a law of physics. One of the laws of physics says that charge cannot just disappear, and so if it goes into the junction, it has to come out.
Yeah, but how did you figure out what went into it? That's my
Which ones were going in and which ones were coming out?
No, yeah, just all together, because didn't the amperage of the whole system stays stable from the beginning to the end?
Yes, but we don't know which ones are going in and which ones are going out, but that doesn't matter if they're going in or out. All we know, all that we have to say is that if it goes in, it has to come out. That's what that junction rule says. So we just choose random directions, just arbitrarily. We just say, we're going to say that this one's coming in, this one's going out, and this one's coming in. And in the end, if it's negative, we just know that we chose the wrong direction, but the value will still be the same. So all we're doing here is creating an algebraic model for what has to happen. And if the current goes into the junction, it has to come out. That is a law of physics. It's never, ever been observed to be otherwise. So that's all that junction rule says. It doesn't tell us what the currents are, doesn't say anything else about the currents, doesn't say anything about the direction. It just says that it has to be there. Like you said, that total current has to remain constant. So that's all that rule is saying. It's just a mathematical expression that shows that that's true. But we can use that mathematical expression because it's an equation. Because it's an equation, it can be used mathematically. So then we just set it aside. And then we choose a direction that we're going around the loop. I just always go clockwise, like I said. And I go around the loops as many as I need to give me enough equations total for the amount of variables that I have to solve for. So if I have 4 currents to solve for, I try to make 4 equations total. If I have 3 currents to solve for, I try to make 3 equations total. And if I'm using multiple loops, I try to use loops that are overlapping each other so that they're connected mathematically. I go through and I use the loop rule to add up all the potentials around the loop so that they equal 0, making sure that I obey the rules for going through resistors against the current and with the current and going through batteries forwards and backwards. And those rules are right up here. If you can't remember them, they show them right here. If you're going with the current, and calculating the potential difference, it's going to be a negative change, negative current times resistance. If you're going against the current, it's going to be positive current times resistance. And then if you're going from the low side of the battery to the high side of the battery, it's going to be a positive EMF change. If you're going from high to low, it's going to be a negative EMF change. If you use those rules to put in the signs correctly into those equations, then those equations will have all of the mathematical information necessary to tell you what the currents are if you solve them properly. And that is what Kirchhoff's laws are all about. And in fact, that's what all circuit analysis is about. This is how you analyze every single electronic circuit in the world. There are other shortcuts that engineers use, but all their shortcuts are based on this process, based on these laws and these rules. They have shortcuts for specific situations, specific circumstances. So that's pretty much it right there. Okay, so that's Kirchhoff. You have a couple of fairly complex circuits at the beginning of your homework for that. In this section, they explain how voltmeters and ammeters work and why they have to be connected in series and parallel and series, rather, respectively. Suffice it to say that voltmeters and ammeters, when they used to be all analog meters, worked on the principle of electromagnetism. And that's something we haven't really discussed yet, but it's the idea that flowing current creates a magnetic field which can then be used to move things. And they don't really show a picture of it here, but I have a picture of it. I have a demonstration one. But what would happen? Let me get my demo model out here really quick. Here's the demo model of what's called a galvanometer, which is the voltmeter ammeter. You can see right here at the bottom, there's this thing with these coils, and it almost looks like the core of a motor or a generator. And that's really what it is. And you would connect this up to your circuit, and current would come in, and it would create a current in that thing and create a magnetic field, and then there's a magnet surrounding that that would deflect this needle. Tell you how much current. And if you wanted to measure voltage, you would use these load resistors on the back, and you would put a load resistor in here, and you would essentially decrease the amount of current going through to almost 0. And in that case, the scale here would change to a voltage scale instead of a current scale.
That's an old-time voltmeter.
It is an old-time voltmeter. And in truth, a lot of electricians still use these because they have a much faster response time than digital ones. So you can see very quick acting voltages with these much better than you can with the digital ones these days. And these ones are much more expensive than digital ones. You can have, I think that a really, really good galvanometer these days can cost $10,000 for a small pocket one, And pocket one is, a stretch. They come in a case, really. So they can be quite expensive. And let me show this to our podcast viewers. So here's my demonstration galvanometer. And here, down here at the bottom is this ring that has these, you can see the copper coils on it. And those copper coils are the thing that the current would go through as you connect your wires down on these plugs down here. And current would go through this and create a magnetic field down here. And there's a magnet. This is a magnet on either side of this. And it would deflect this meter up top. It would deflect this needle to tell you how much current was going through. And if you wanted to measure voltage, right here you'd put in a resistor to decrease the current, and that would scale this thing up here to measure voltage, essentially. And you could also use, there were also some shunt resistors back on the back that you could use so that you could change the scale to measure different amounts of voltages and different amounts of currents. You had to have a much higher understanding of electronics to use this device, but it does give us an idea of how these things work. A voltmeter, you don't want current to go through it. You want as little current as possible to go through it. And that's why they would put in that resistor down here to block that current. And so in voltmeters, you don't have current going through, and you're just measuring that potential difference across an element of the circuit by wiring it in parallel with that element of the circuit. But with a current meter, you want all the current to go through this little coil down here, but you want it to have as low resistance as possible. And so you would configure this device to have as low resistance as possible, so it wouldn't affect the circuit, but it would still deflect this meter as much as it needed to show you the current. And that's why the current meter was put in series, is because you wanted all the current to go through this so that you could actually measure that current as accurately as possible. And that, in essence, is what they're talking about in this next section. And the problem with them is that they do have these meters do have limitations, because an ideal voltmeter has infinite resistance, but you can't make infinite resistance and still have this thing work. This thing requires some current go through it. So this thing was not an ideal voltmeter, but it was a good voltmeter in certain situations, as long as your resistance of the galvanometer was much higher than the resistance that you were measuring the voltage across in the circuit. But it also wasn't a perfect ammeter, because ammeters you want to have zero resistance. But this thing, since it's going through a wire, has some resistance. So there was always some give and take with galvanometers, and it's also true with digital multimeters. You always have some give and take. There's always some limitation, and you're always got some error in your measurement. And so galvanometers and ammeters, and multimeters, both have an internal resistance like batteries do, and that internal resistance can affect your measurement. And in order to avoid that, or in order to minimize that effect, that's where we get into this idea of using shunt resistors and other things. So the one of the uses for the resistors that are built into that you can use with this thing is to split the current so that you get a known current going one direction and a known current going the other, and whatever the other current is going the other direction. Or to get as little current going one way and as much current going the other way, or to split the current exactly. There's lots of different ways to do that, and they're just showing different ways to accomplish this. And they don't really have a lot of we don't really have a lot of calculations to do with that. So I'm not. I don't think I gave you any homework involved in that, for example. That's much more important for people who are doing precision electrical measurements. It's not something we take much into account anymore, just for your everyday electrical measurements. Very few people have to deal with it. Okay, so now we have null measurements. This is another way that we can measure currents and resistances and voltages and other things. And this uses what we call a Wheatstone bridge, which takes advantage of a potentiometer, which is the variable resistor that you used in the lab yesterday. And in this case, you build this Wheatstone bridge, which looks like this. It's got two paths for the current, and one path goes through this variable resistor, which is your balancing resistor. It allows you to adjust things so that you can balance this thing out. And then it goes through this unknown resistor, which is the resistance you're trying to measure. And then it goes through another set of resistors over here that are well known and well measured. And then you have your galvanometer in the middle that is going to measure the current going through here. And the idea here is to balance this resistor until the current going through here is 0. And that means that the voltage here and the voltage here are exactly equal, or as exactly equal as you can get them. And then you can use this equation that they've developed here to calculate that other resistor, that unknown resistor, R sub x. And so it's a very, very useful tool. And in fact, this is built into, they have one of these built into your multimeter when you're measuring resistors. When you're measuring resistors with a multimeter and you switch to that resistance setting, it actually switches to a Wheatstone bridge with a variable resistor that changes automatically to make sure that there's no current going from this side to this side. And then it does the calculation and tells you the resistance of that resistor. Without a Wheatstone bridge, measuring the resistance of a resistor is affected by having the resistor you don't know in it. And so it messes things up. But this one doesn't. This one takes that out of the equation by balancing the current on either side exactly with this variable resistor. So it's a very useful tool, and there are many varieties and uses for the Wheatstone bridge. Many different uses of it, many different varieties of it, different changes that you can make to it, and different things you can do with it. And that's just the first one that we show to you as a nice practical use of this knowledge that we are so freely giving to you. Okay, so now at the end of all this, we're going to add capacitors into the mix. I believe this is the end of chapter 21. Let's check real quick. Yep. So at the end of this, we're going to add in capacitors into the mix and figure out how they are affected by things. And the really interesting thing is that current doesn't pass through a capacitor when it's direct current. And so something interesting happens. If we put a resistor and a capacitor in series with a battery like this, what will happen is that the current will flow out of the battery through the resistor and towards this side of the capacitor, and will build up a bunch of positive charge on this side of the capacitor, the top of this capacitor. On the other side of the capacitor, as the positive charge is building up on that other side, that one side, on this bottom side, positive charge is going to start running away from that buildup. And so this one's going to start getting negatively charged as positive charge runs away. And that positive charge, of course, is going to go back towards the other side of the battery. So what this does, what this configuration does, is it charges your capacitor, plain and simple. It charges the side that's on the positive side positively, the side that's on the negative side of the battery negatively, and it drives a current through the resistor during the charging process. But eventually this capacitor is going to reach its full capacitance. You won't be able to push any more charge onto it. Remember that for every capacitor that's put at a certain voltage, there's only so much charge it can hold. And once it gets to that amount of charge, it stops holding charge. And so this is what you're going to see in time. As time goes by, when you first connect it to this battery, or you first flip this switch so that the circuit is complete, you're going to see a lot of voltage build up on that capacitor. So the voltage is going to start at 0 when you flip the switch, and that voltage is going to build up really, really quickly. But as it goes on, there's going to be no more buildup. It's just going to zero off, or the amount of buildup is going to reach a maximum point, which is going to come close to the EMF of the battery. So the capacitor's voltage at the end of this, at the end of a long time, will equal the voltage across the battery. Now, the time that it takes to do this is something that we can calculate, because this is a function that is known. And here is the function for a charging capacitor with a resistor in series. the voltage buildup on the capacitor is equal to the EMF of the battery times the quantity 1 minus e to the minus time over resistance times capacitance. So the time is measured in seconds, the resistance in ohms, the capacitance in farads. If you plug in the value of the resistor and the value of the capacitor into this equation, and then however much time you've let go by, then you will know how much voltage is built up on the capacitor. And this is the shape of that function. This amount of time that it takes this capacitor to get to this point right here, 0.632 times its total voltage, or 0.632 times the voltage of the battery, is what we call the time constant of this circuit, and it is equal to the resistance times the capacitance. The resistance in ohms times the capacitance of the capacitor. So each resistor-capacitor combination will have a different time constant. In other words, it'll take a different amount of time for it to charge up. If you want your capacitor to charge up very quickly, right, then you need a small resistance and a small capacitance. However, if you have a small capacitance, you're not going to have a lot of charge. So if you need a lot of charge and a small time constant, then you need a big capacitance and a small resistance, right? So there's a lot of different ways you can mess with this to make this work out for you. Bottom line is if you need a lot of charge built up, it's pretty much going to take you a lot of time, no matter what. And that's why on cameras, especially old school cameras that used a xenon flash bulb, you had to wait for the flash to build up. It'd take time for that to build up, and you'd hear it building up. And that whine that you would hear was actually the circuit charging the capacitor that was going to be used to flash that light bulb. So the time constant on most of those flashlights was a few seconds, at least. Bigger the flash, longer the time constant. Bigger the capacitor, longer the time constant. If you want to discharge a capacitor, you take that charged capacitor out of the circuit that has the battery in it, and then you connect it to the resistor that you want to discharge it through. This might be your flash bulb, for example. And then you put a switch on it, you put a circuit on it with a switch, and when you want to discharge it, you flip the switch, and then all that charge is built up on the one side is going to just jump off and try to jump through that resistor and go to the other side and balance out. And the amount of time that it takes to have a 60% discharge from from maximum voltage down to 0.368 voltage, so it's 63%, is also the same time constant, resistance times capacitance. So that is also used for discharge. But the equation is different, and the functional shape is different. Here's the equation for the discharge, the total voltage times e to the minus t over r. See, it doesn't have that 1 minus thing in there. So, again, these two equations, these two functions for charging and discharging, use time in seconds. This little t up here is time. If you're not familiar with the e here, this is the natural exponential thing e, which is like 2.3, 2.71, so I don't know what it is. Some value that comes from statistics. But anyway, it's a number that your calculator has. It should just be a little script e on your calculator, and then it puts whatever you put after that into the exponent of it. So all this stuff is in the exponent. That t is in seconds after you've started charging, or in seconds after you started discharging. So here we're going to calculate the size of the capacitor of somebody who is needing a very, very fast photograph. So they're using essentially the time constant here. This time constant, tau, equals R times C. They know the resistance of the flash bulb, and they need to calculate the capacitance that they're going to use. And they also know the time frame of the velocity of a bullet. So they're doing a bullet through something, and then they're going to calculate the capacitance of that. So the first thing they do is calculate how small the time has to be, and then that has to be equal to their time constant. And then their capacitance is going to come from solving the time constant for the capacitance and plugging in the resistance. Get 16 microfarad capacitor to do that. My grandfather used to do pictures like that. Okay, so I'm going to take a little bit of a break right now, and I'll be right back, and then we'll come back and talk about this next example. Okay, sorry about that. Back in the saddle. Okay, so heart defibrillators also use capacitors that are charged and then discharged through the body, right? So here's the circuit diagram. Here's the circuit diagram for a defibrillator. You have your power source over here, battery, usually for a portable one. Goes through a resistor and charges up this capacitor. And while this switch over here is closed, that capacitor is charging, right? Actually, is that the right one? Sure, why not? Yeah.
Discharge.
So this is actually the circuit diagram for a flash bulb, but it's the same idea as it's the same idea as a heart defibrillator. So when this switch is closed, it's charging the capacitor as current flows through here. Why won't it flow over here? Over here, you have your electrodes that are connected to the body, which has high resistance. So not much current's going to want to flow over here. Current's just not going to want to do much over here. However, once this thing gets fully charged, it's getting a higher and higher voltage across this. And this over here, these electrodes over here are designed so that the current will want to flow through here once that charge is high enough. Or you can put another switch over here, which is the case of a defibrillator. With a flash bulb, it can be either way. But in the case of a defibrillator, they just put another switch over here so that when this is fully charged up, they flip this switch open so that this charged capacitor is just sitting here charged. And then when they're ready, they flip this switch closed and the charge will travel from here through the body of the person. And that's how it works. So in this case, in the heart defibrillator, we have a certain amount of time that we want to apply our charge in, or let's see here. Well, they give us but they've given us the resistance and the capacitance actually here, it looks like, and they want us to calculate the time constant, first of all. Time constant is R times C, of course. That's 8 milliseconds. And then we're going to calculate the amount of voltage change for the first 8 milliseconds in that first time constant. So we go to plug that into our equation, and in that equation we're going to get, and we plug it into the equation for where we know that first time constant, we get down to 0.368 of our original voltage. So that gives us 3.68 times 10 to the 3 volts if we started with 1,000 volts or 10,000 volts. We would get down to this voltage. So if we started at 10,000, then we get down to this voltage after the 8 milliseconds. Then if we want to know how far we get after 16 milliseconds, then we do this again with that voltage that we just calculated. So we take this voltage and plug it in as V0 again, do it twice, and that's what they do here. And then we get 1.354 times 10 to the 3 volts, so 1,300 volts at 16 milliseconds. So every time you go through a time constant, you lose another 60% of your voltage, and you only get through 36% of it, 0.368. So that's what the time constant is good for, is it tells you that every time constant that passes, you lose 63% or 63.2% of your voltage, and you use that equation to do that. So then after 24 milliseconds, you do it again. You take this voltage that you calculated here, multiply it by the 0.368 again, and you get 498 volts after 24 milliseconds. And you want that big voltage drop in that short time for a defibrillator so that you get a very quick energy jolt to the heart. You don't want it to be too long, because if you have a long energy jolt, then you have a long a long time that current's going through, and it'll cook your heart. But if it's a very short time with a very the right voltage and the right current for a very short time, doesn't have time to cook anything, it just gets things started again. And that's the idea. So that takes us through chapter 21, and we have, significant amount of time to answer questions. If you have questions about the homework, if you want to work on homework and then ask questions, or if you have a question right now about the homework, that'll be fine too.
Got a question
What's your question?
about problem number 1, I believe. Yes. Very first problem. So it doesn't give us any of the resistances for the light bulbs or the resistors. Similarly, you're supposed to be able to take the
It's true that it doesn't give you any of the resistances, but it does give you 4 of the currents. So you don't even have to know all the currents.
right, but
Okay, so here's
how do I know what's I1?
so in this case the current I1 is the current through L1. So each one of these has a different number associated with it. So current I1 goes through L1, I2 goes through L2, I3 goes through R3, and so on.
Some of all of them should be 0?
No. What does the junction rule say?
Current has to stay the same.
Pseudo-junction.
At each junction, the currents going in have to equal the currents going out. So here's a junction right here.
I assume, and yeah, I did that. So I assumed on that one that current 1 is going in, and that it comes out of currents 3 and 2. At currents 3 and 2.
So current 1 is going in. That means the current all the way through here is going this way according to your assumption. That means the current from this one is going out this way, and the current from this one is going out this way. Now you have to keep those things that way if you want these currents to work out for you. And that's fine. So that gives you one equation, but it doesn't tell you everything because the only current in those 3 currents that you know is I1.
Right.
So that's 2 unknowns and 1 equation. So make another equation. Come here to this one. This one, you've already said that R3 was going out of this one. So it's going into this junction here, right? And you can choose some directions for these two, join these two, and going out or in or whatever else, and then make a new equation. And then make a new equation for this junction.
Okay, just keep making equations.
Make a new equation for this junction. Make an equation for every junction that is unique. And then with all of those equations, you should be able to manipulate them to start solving for currents.
Right.
And then eventually you should be able to solve for all of them.
Can you print mine out?
Print your homework out? Yeah, you can do it in the next room. I can't do it from here, so yeah, you can just sign in and print it off. Now in this case, they've given you voltages. So you create voltage loops and voltage equations using the second rule, and you fill in the blanks that way.
Need the keys to the kingdom.
Okay.
That one I can use the voltage across the voltage drop across the resistor. So.
Yeah. All right. Any other questions?
No.
Good to go.
Just the first 2.
Okay.
Because I was expecting a question that was kind of a combination of the 2.
Yeah, and they didn't have one already made, so and I didn't have time to make my own because these questions have just become available, and since I'm just using this for the first time this year, I haven't had time to write my own. Eventually, I'll write my own questions and have one that's more complex. And
It's not a bad thing, you just learn from.
yeah, what kind of loop? Clockwise or counterclockwise? All right, so we'll end our recording at this point, and if you have questions about the homework, contact me. When is the homework due? Today or tomorrow or something? I don't know.